Welcome back. Today we're diving into something I think many of us working with large AI models have bumped up against.
Oh yeah, what's that?
Well, how do we get these incredibly smart models, the ones that can really reason through tough problems, to actually do it efficiently, without needing a supercomputer or taking ages?
Ah, the classic speed versus depth problem.
Exactly. And we're looking at a really neat paper today that tackles this, specifically this weird issue where models can sometimes get less accurate if they overthink a problem.
Right, it's like they get lost in their own thoughts.
Totally. The paper is called Dynamic Early Exit in Reasoning Models. And the core idea is this training-free method they call DEER, D-E-R.
DEER? Okay.
Okay? And what it does is it lets these large reasoning language models, or LRLMs, stop reasoning early. Right when they've got just enough info to get the right answer.
So no unnecessary extra steps.
Precisely. Think of it as a smart efficiency boost. And here's the kicker. It often actually improves accuracy, too.
Okay, now that is interesting. Less work, better results.
Yeah. Across math, science, programming.
Yeah.
They saw average cuts in those reasoning chains of like 31 to 43%.
Wow.
And get this, for programming tasks, it was almost 65% shorter reasoning.
65%, that's huge.
It is. Plus, accuracy bumps 1.7 to 5.7% on reasoning, and a solid 2.1 point jump for code correctness. That pass at one score.
Okay, you've got my attention. Less compute, sometimes better answers. How does it work?
It's our mission today.
Oh.
We're going to unpack DEER, look at how it works under the hood, check out the evidence, and think about what this means for making AI reasoning more practical.
Absolutely. Let's start with that overthinking thing. What does that actually look like for an LRLM?
Well, the paper gives some good examples.
Yeah.
We tend to think more steps, deeper reasoning. That must be better, right?
Usually, yeah.
But these models can generate these really long, sprawling chains of thought. And sometimes they just introduce irrelevant stuff or wander down a completely wrong path.
Getting sidetracked.
Yeah, exactly. They can get so tangled up in the process that they actually miss the clear answer they might have had earlier on. It's like they talk themselves out of the right solution.
Right, like adding extra steps to a math problem that just confuse things.
That's a great analogy. The paper even shows specific cases where the model just keeps generating text, but it's not getting closer to the right answer. Sometimes it's actually getting further away.
Okay, so how does DEER know when to step in? To do that, we probably need to understand how these models typically reason first.
Good point.
The paper describes this pattern. They call it slow thinking, which leads to a final conclusion. This slow thinking involves, generating thoughts step by step, often with special markers separating them.
Like delimiters.
Exactly. And they also identify these thinking chunks. Things like first understanding the problem, then exploring different ways to solve it, and finally checking the result.
Makes sense.
And crucially, they pinpoint these action transition points within the reasoning, often signaled by words like wait, or alternatively, maybe These are moments the model seems to pause or shift its strategy.
Ah, okay. So it's like the model leaves little clues about where its head is at. Which brings us to this idea of Pearl reasoning. Sounds cool. What's that?
This is really central to the paper's idea. Pearl reasoning is basically that sweet spot, the exact moment in the model's thinking where it has just enough information to get the right answer. Not too little, not too much.
The Goldilocks point of reasoning.
Kind of, yeah. And their analysis found that for about 75% of the problems they looked at, this Pearl moment actually exists within the reasoning chain.
75%. Wow.
And here's the really surprising part. For some questions, stopping early at that Pearl isn't just faster. It's the only way the model gets the right answer.
Wait, really? If it keeps thinking, it gets it wrong.
That's what they found in some cases. They point to specific examples where the model reasons past the Pearl and ends up making a mistake. It's like the extra thinking just adds noise or confusion.
That's fascinating. So the model can literally reason itself away from the correct answer.
It seems so. They even did a small test, applied early exit to 30 samples, got an 11% accuracy increase, and cut the compute cost by 40%.
Okay, that's a powerful argument for finding that Pearl. So we know overthinking is bad. We know about these thinking patterns in the Pearl moment. How does DEER actually find the Pearl and tell the model to stop?
Right. So DEER uses three main modules working together. First up is the reasoning transition monitor.
Okay, what's that doing?
It's basically watching for those action transition points we talked about, the wait, alternatively, moments. These are flags, potential spots where the model might have figured things out already.
So it sets up checkpoints. Got it. What happens at a checkpoint?
That's when the Answer Inducer kicks in. When the monitor flags a transition point, this module basically asks the LRLM, okay, based on everything you've thought so far, take a shot at the final answer.
It prompts it for an intermediate answer.
Exactly. And they use specific delimiters like boxed to make it clear this is a trial answer. The paper writes it as A equal LRLM PTI. The answer A is generated by the model given the problem, P, the thought so far, T, and the inducer's prompt, I.
Clever. So it's like a quick probe. Think you've got it yet? How does it know if that trial answer is any good, though?
That's the third module, the confidence evaluator. This one looks at the trial answer the inducer just generated and calculates how confident the model seems to be about it.
How does it measure confidence?
It looks at the probability the model assigned to each token, each word in that trial answer, specifically the maximum probability predicted for each token. Then it averages these maximum probabilities across the whole answer to get one confidence score, C.
Okay, so it's getting a numerical score for how sure the model feels about that intermediate answer.
Precisely. The math is in equations 2 and 3 in the paper, using the model's softmax outputs.
Right, so we have a confidence score. What's the final step? How does it decide? Stop or keep going?
Simple comparison. DEER compares that confidence score, C, against a threshold value they call Lambda. This threshold is set beforehand, empirically.
Okay.
If the confidence C is higher than the threshold, DEER says, okay, looks like we hit the pearl, and triggers the early exit. That trial answer becomes the final answer.
And if it's lower?
If C is below Lambda, DEER figures the model isn't confident enough yet. So it tells the model, nope, keep thinking. And the LRLM goes back to generating the next chunk of reasoning from where it left off.
Makes total sense. Set a bar, see if the answer clears it. Now, you mentioned something about acceleration. Branch parallel decoding sounds a bit complex.
Yeah, it addresses a potential issue. Doing that answer induction and confidence evaluation takes a little extra time, right? Which could eat into the savings from shorter reasoning.
Right, you don't want the check to take longer than the time you save.
Exactly. So branch parallel decoding is a way to mitigate that. The basic idea is to try and do things simultaneously. Instead of reason, pause, induce, answer, evaluate, maybe continue reasoning.
Yeah.
It tries to overlap the induce, answer, and evaluate part with the next step of the regular continue reasoning part. They use some clever techniques with attention masks and managing the model's memory, the KV cache, to sort of run these two branches and potential early exit path and the continued reasoning path somewhat in parallel.
Okay. So it's trying to hide the latency of the checking process by doing it while the model is already starting its next thought.
Pretty much. It helps keep the whole process snappy.
Cool. Okay, we get the mechanism now. Let's talk proof. What kind of tests did they run?
They really put it through its paces. 6 different benchmarks. For math, they use Math 500, that one's notoriously hard, plus AMC 2023 and AME 2024.
Okay, challenging math problems.
Yep. Then for science, GPQA Diamond, which covers physics, chem, bio, also very tough, and for coding, Human Evil, and Big Code Bench. So a good mix of domains and difficulties.
And which models did they test this on?
Primarily the DeepSeek R1 Distill-Kuhn series. These are models ranging from 1.5 billion parameters up to 32 billion. They're distilled versions, fine-tuned specifically for reasoning.
So models built for this kind of task.
Right. And they also used QWQ32B, another strong reasoning model, just to double-check the results weren't specific to the DeepSeek architecture.
Good thinking.
Yeah.
And the key metrics, what were they measuring?
The main ones were accuracy, ACC, did it get the right answer? And generation length, LENN, basically, how many tokens did it generate, which is a proxy for computational cost.
Makes sense.
And for the coding task, they also used pass at 1. Does the generated code pass the tests on the first try?
Right, standard for code generation. Okay, drum roll, the results. What did they find? Was DEER actually effective?
Yes, consistently effective. Across the board, looking at Table 1 in the paper, DEER delivered really significant cuts in reasoning length, generally between 31% and 43% on those reasoning benchmarks.
That's substantial. But what about accuracy? Did it drop?
That's the amazing part, no. Accuracy generally improved. On average, they saw gains between 1.7% and 5.7% on those same reasoning benchmarks.
Less thinking, better answers. That really drives home the overthinking problem, doesn't it?
It really does. And these benefits showed up across different model sizes, too.
Any specific highlights? Where did it shine most?
Well, the smallest model, the 1.5b parameter one, got a huge 4.8 percentage point accuracy boost on Math 500 while using only about half the compute.
Wow, making the small model punch way above its weight.
Kinda, yeah. And on the other end, the big 32B model saw a massive 10.6 point jump on GPQ Diamond and 6.6 points on AIM 2024 with DEER. So it helps both small and large models, though maybe in slightly different ways.
Interesting. The paper also dives into a fine-grained analysis using Figure 5. What did that show?
Yeah, Figure 5 is great. It breaks down every problem into 4 categories. Did standard code get it right and DEER get it wrong? That's bad for DEER. Did DEER get it right when standard code failed? That's good. Or did both get it right or both get it wrong?
Okay, comparing hits and misses.
Exactly. And the key takeaway visually is that the green bars, where DEER fixes an incorrect answer, are generally much bigger than the red bars, where DEER causes a correct answer to become wrong.
So it's correcting more errors than it's introducing.
That's the picture it paints, yeah. Especially for the math benchmarks. It's strong evidence against the idea that just stopping early is inherently risky.
And did this analysis confirm anything about smaller models overthinking more?
It seemed to suggest that yes, the proportion of those green bar cases where only early exit worked tended to be higher for the smaller models. This kind of hints that smaller models might be more prone to getting lost if they reason for too long.
Huh.
They also saw that overthinking seemed more common on the harder problems, which intuitively makes sense.
Yeah.
More complex problem, more potential paths to explore, more chances to go wrong.
So DEER might be particularly valuable for making smaller, more efficient models behave more like their larger counterparts by cutting off that detrimental extra reasoning.
That's definitely one exciting implication. The paper even talks about the performance ceiling, suggesting if DEER could be even more precise in hitting that pearl moment, avoiding those red bar errors, smaller models could potentially match or even beat larger ones sometimes.
That would be a game changer for accessibility.
Yep.
Okay, what about the programming tasks? Human Eval and Big Code Bench.
Significant results there too, especially on length reduction, as shown in Figure 6b. We're talking 62.7% shorter on Human Eval, 67.1% on Big Code Bench, using DEER with a specific threshold of 0.97.
Huge savings. And accuracy, pass at 1.
On Human Eval, with that 0.97 threshold, they also got a very nice 4.3 point improvement in pass at 1. So again, faster and more correct.
It really seems like that threshold, Lambda, is super important. How sensitive is DEER to that value?
Very sensitive. Figure 6a illustrates this well. If you set Lambda too low, DEER gets too eager, exits too early, and accuracy can drop because the model hasn't reasoned enough. But if you set it too high, it gets too cautious, waits too long to exit, and you lose out on the efficiency gains. So finding that sweet spot for Lambda is crucial. It needs careful tuning for a given model and task.
Makes sense as a balancing act.
Yeah.
The paper also includes a case study, right, to make this more concrete.
Yeah, Figure 9 has a great example from Math 500. Both regular chain of thought and DEER get the first critical step right.
Okay.
But then the standard method keeps going. It starts double-checking, exploring alternatives, gets confused by some intermediate results, and it actually fails to give a final answer. It gets stuck.
It overthinks itself into paralysis.
Pretty much. Whereas DEER sees the high confidence after that first correct step, says, looks good, exits early, and delivers the right answer. Perfect illustration of avoiding the overthinking trap.
That really shows the benefit. Any other examples like that?
Yes. Figure 10 shows a double summation problem. Again, both methods get the first key insight. DEER stops there. Correct answer. The standard method continues, adding redundant summaries, just generating more think tokens without adding value. Figure 11 shows this with QWQ32B2, lots of extra thinks tags and summaries.
It's spinning its wheels, basically.
Exactly, wasting computation and risking errors.
Fascinating. Okay, before we wrap up, how does DEER stack up against other ways people have tried to make reasoning more efficient?
Good question. The paper groups related work into things like post-training methods, prompt-based methods, and output-based methods.
What's the difference?
Well, post-training might involve fine-tuning the model specifically to be more concise, maybe using reinforcement learning. Prompt-based methods focus on writing clever prompts to guide the model to a shorter answer. Output-based might involve generating multiple answers and picking the shortest good one, or stopping generation early based on some criteria.
And DEER?
DEER stands out because it's training-free. You don't need new data or model tuning. It slots right into the existing chain of thought process. They mention some concurrent work aiming for similar goals, but those often need extra components, like another model just to check the reasoning quality. DEER lets the main model sort of self-assess its confidence.
So it's potentially easier to implement and integrate.
That seems to be a key advantage, yes.
Okay, this has been a great exploration. To boil it down for everyone listening, what are the absolute key takeaways about DEER?
I'd say number one, DEER can significantly cut down the computational cost, the length of reasoning in LRLMs. Number two, surprisingly, it often improves accuracy at the same time by stopping the model from overthinking.
Less is more sometime.
Exactly. And number three, it achieves this without needing extra training, making it a practical tool you could potentially apply to existing models fairly easily across different tasks, math, science, code.
And looking bigger picture, what are the implications here? Why should people care about techniques like DEER?
Well, it tackles a major hurdle for actually using these powerful reasoning models in the real world. If you need an answer quickly or you have limited computing resources, making reasoning faster and cheaper is critical.
Right, it makes complex AI more deployable.
Yes, and the fact it can also improve reliability by cutting down on errors caused by overthinking is a huge bonus. It's about making these systems not just smart, but also efficient and dependable.
For listeners who want to get into the real technical meat, the specific results, the math, where should they look?
Definitely check out the original paper, Dynamic Early Exit in Reasoning Models. It's got all the detailed results, the setup, the analysis, and they discuss future directions too, like getting even better at finding that pearl moment or making the threshold adaptive.
Excellent. Well, that brings us to our final thought for you, the listener. As we develop AI that can reason more deeply, how might techniques like this, dynamic early exit, fundamentally change how we even think about designing and measuring AI intelligence? Could this be a step towards AI that's not just powerful, but also resource-aware and knows when it's thought enough for the task at hand?
A fascinating question. Does intelligence require exhaustive processing or knowing when to stop?
Something to chew on. Thanks for joining us for this deep dive.